Welcome back. In this video, we are going to solve example 4.5 that is taken from chapter number 4, Axial Load, and book name is Mechanics of Material by RC Hibbeler, 9th edition. So statement is the aluminum post shown in figure is reinforced with a brass core if this assembly supports an axial compressive load of 9 kips applied to the rigid cap. Determine the average normal stress in the aluminum and brass. Take aluminum modulus of elasticity is 10 into 10 raised to power 3 ksi, and for brass it's 15 into 10 raised to power 3 ksi. So you can see this is aluminum post that is reinforced by a brass clear core, and they are here there is a rigid cap which hold these two together, and there is a point load of 9 kilonewton or axial load is applied. The radius of this brass core is 1 while aluminum core radius is 2 inch. The length of this post is 1.5 feet. So you have to determine the stress in this aluminum post and the stress in this brass core. So let's start with the solution. So as you can see, there is a 9 kips load is applied. So this support will apply a reaction force on this brass core as well as on this aluminum core. So for that we will draw the free body diagram. So I have drawn it over here. So you can see this is 9 kips load, and the reaction offered on this post is some of the load is taken by the brass while some of the load is taken by the aluminum. So if you apply the equation of equilibrium, that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. So from this minus 9 plus F of aluminum plus F of brass is equal to 0. So we can say F of aluminum plus F of brass is equal to 9 kips, and this will be our equation number 1. And you can see that this problem is statically indeterminate. Why? Because you can see we have two unknown and we have this only one equation of equilibrium. So by using this we cannot find any of this force. So what we will do is that we will use compatibility equation. So how we will find this compatibility equation? As we have been given that it is applied to the rigid cap. So there is a cap, rigid cap, which will cause this aluminum as well as brass core to move downward because these are in compression. So they will move downward. So the rigid cap at the top of the post causes the aluminum and brass to displace the same amount downward. Therefore, we can write as the displacement of aluminum will be equal to displacement of brass. So what we will do is that we will write the equation for both. So for aluminum it will be equal to F of aluminum into length of aluminum divided by area of aluminum into E of aluminum, and that will be equal to F of brass into length of brass divided by area of brass post and modulus of elasticity of brass. Okay, so from here what we will get is, if I get this F of aluminum, so F of aluminum will be equal to F of brass multiplied by area of aluminum divided by area of brass multiplied by length of brass divided by length of aluminum. Since length of brass is equal to length of aluminum is equal to L, so they will cut with each other. So we will left with F of aluminum will be equal to F of brass multiplied by area of aluminum divided by area of brass. Okay, now put the value of this area. So F of aluminum is equal to F of brass, so area of aluminum. So you can see that this aluminum is having outer radius is R naught is 2 inch and inner radius is 1 inch because this is a tube like, clear? So 1 inch. So area will be equal to pi r square r naught r naught square minus r inner square. So I can write it pi multiply by 2 square minus pi into 1 square, pi into 1 square, or you can also write it as pi multiply by 2 square minus 1 square, divide by what is the area of brass. So it will be, you can see the brass core is solid having radius of 1 inch, so I can write it as pi into 1 square. Okay, when you solve this you will get F of aluminum will be equal to 2. Okay, one more thing I left is that here we also have E of aluminum divide by E of brass. Okay, so multiply by E of aluminum is how much? E of aluminum is 10 into 10 raised to power 3. 10 into 10 raised to power 3 divided by E of brass, which is 15 into 10 raised to power 3. So when you solve this, you will get a F force in aluminum post will be equal to 2 times force in brass. Okay, this is your equation number 2. Now put equation 2 in equation 1. So what is equation number 1? Equation number 1 is this one. So I can write 2 times FBR plus FBR is equal to 9 kips. So it means 3 FBR is equal to 9 kips, and from here you will get FBR will be equal to 3 kip. Once you get this FBR, plug this value, put FBR is equal is equal to 3 kips in equation 2. You will get this force in aluminum post comes out to be 2 multiplied by 3 is equal to 6 kip. So force in aluminum post is 6 kip. Now we have been asked to find the stress, average normal stress in aluminum and brass. So what we will do is that we will write stress in aluminum post will be equal to force in aluminum divided by area of aluminum. So force is 6 kips, so 6 into 10 raised to power 3 divided by area is pi r naught square minus r inner square. So r naught is 2 square minus r inner is 1 square. So when you solve this, you will get 0.637 kips. This is stress in aluminum. Now what will be the stress in brass? So it will be equal to force in brass divided by area of brass. So force in brass is 3 kips. So 3 into 10 raised to power 3 divided by area, which is pi r square. So r is 1. So when you solve this, you will get stress in brass comes out to be 0.955 KSI. Okay. So these are the answer of our this question. Now if you want to represent on the element, so you can see this is the initial, this aluminum post, and this is brass post. So if I project this this area over the above, so we can see that this stress is compressive. So stress in aluminum is 0.165. So if I draw lines from this till this surface, on this surface, on outer, similarly downward here you can see all these forces will be, this red one will be compressive stress in this aluminum post, and this stress in aluminum will be 0.637 kip. Similarly, if you want to have this stress in brass, so it will be like this. So this black lines will show you the stresses in aluminum core. So this will be the compressive stresses, and the arrowhead will be downward because it will show the compressive stress. So this is brass, stress in brass, which is 0.955 KSI. So using this result, the stress distribution is also shown in this figure. And that was all about this example 4.5. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.